J180 with Z naught is 100. You all see the class? All right, now move this out of here. If I want to do that, what I can do is this. I have 50 plus J180, so that's the spot. When you normalize it, divide by 100, that's the spot you come into. You all can see that, can't you, class? Right? It's so if you take 50 plus J180 at 100 ohms to normalize, you're going to get 1/2 plus J 1.8. That's this point right here. The next step, you draw a circle that goes all the way around, and the radius would be from the center point to the point where Z, the normalized impedance, is. And then you go to the admittance point, right here. You all see this, class? I mean, can you see my screen? I can't tell if you just thumbs up. Give me some indication. Okay, good, good. All right, now the next step after that is you move from this point to the point right here where you have 1 plus J something. You all see that? This is going to be the minimal distance from the actual load to the point where you attach the stub. Then the next step is attaching a stub. Now a stub is admittance, so if it's a short circuit stub, it starts here. If it's open circuit stub, it starts here. And this one was open circuit. And actually, well, now you go down to there, and that's what the actual path would be for the total parallel impedance. All right, a second. This is another possibility. This would be a longer length from the actual line, or D would be longer, but L would be shorter. And if you see here, let me go back. So you want the minimal length from the stub, so that would be this, the second one. Oops. Not that one. This one. All right, it hits that point. So we've traveled more than half a wave or a quarter wavelength away. And then you can see from here, you're going to have a ZL, I mean a YL of 1, or 1 minus J 2.6497. Can you all see where that cursor is pointing right here? You all with me? All right, now at that point, we have to get rid of this minus J 2.64. You're going to come in, and it's an open circuit stub here. You're going to have to find plus J. And it talks about the stub length being 0.1216 lambda from here to here. Unfortunately, it doesn't show the stub itself here. The second solution is ours. So and I'll put this, I'll make this available to you. This is a little Smith chart calculating thing that I have. And I'll put these solutions up here, okay? Are you with me on this? The idea would be the second one if you minimize the length of the stub because it's open circuit. Everybody understand why? Because when you come in, if it's an open circuit stub, you're actually going to come in and be at, when you come in, your load or your normalized impedance is here, you go to the opposite point, YL. Now, when you know you're going to have an open circuit stub, so an open circuit stub has an infinite impedance, that would be here, and the admittance would be over here, it'd be 0. And if you're moving from here to make this minimal distance, you want to have positive values that you have to add. which means you want your normalized admittance to have a value of 1 minus J something. And I hope you're getting what I'm saying. This is the first solution. This is the one you don't want. That's 1 plus J something. This is the one we want. It goes to 1 minus J 2.64. And then the length of this stub right here is going to be
that length of that stub is considering it as a short circuit stub. Is that correct?
I can't hear you, Tyler. Could you turn your...
It looks like the length of that stub is if it is a short circuit. Is that correct?
No, this is open circuit.
Right, but like...
I mean, for open circuit, it starts here.
Right, but the 0.44 lambda...
No, that would be, you subtract the quarter wavelengths from that.
Okay.
Yeah. I'm sorry about that. Yeah, you're right. By the way, it's hard to hear you.
I'm sorry, I'm on my laptop, so...
All right.
It'll work.
And I'll post those solutions and I'll make it clear. That's the first problem. The second problem is, this is the one that used Gauss's law to find the D field. This is actually a homework problem. The only thing I did is change rho V slightly. So I'll go to a document camera on this one. And first we have rho V equals 10 to the minus 9th R for R less than or equal to A and 0 else. And I'm going to share, I've got to get my document cam. But you have that, and I've written it down. And then the camera is connected, it's just not working. I got to turn this off and on again. Well, okay. So for this one, I hope you all can see this right here. I have rho V equals 10 to the minus 9th R for R less than A and 0 for R greater than A. Everybody all right with that? By the way, how many people do we have in here right now?
There's 8 of us.
So we're missing a few. Okay. Well, what I'm going to do is just say this, that I have some radial distance A, and inside A I have rho V. Now I know Gauss's law says that the integral of d dot ds over any closed surface is equal to the integral of rho V dV over the volume. So the integral of the surface area dotted into D is equal to rho V dV. And this is a classic problem. This side always is just going to be, if I come out a distance R, not rho, and I put a surface in there, it's called a Gaussian surface. When I integrate around d dot ds that, I'll always get, if it's spherical, 4 pi r squared times d of r. Everybody okay with that? That's just the surface area times d, and d will be a constant value, constant magnitude, and it'll be pointing in the radial direction. The formal way to do this is put d of r, ar, and put ds as r squared sine theta, d theta, d phi, ar. But I omit that because it always comes down to this, and we've done it many times. Okay, everyone? And that's equal to this. Now this integration, I'm going to go ahead and put it up here. Is going to be a triple integral of rho v, so it's 10 to the minus 9th r. And it's going to be multiplying the differential surface. And the differential surface in spherical coordinates is r squared sine theta, d theta, d phi, dr. Everybody with me on that so far? And then, hang on for 1 second. And then the next thing we do is put limits on. Now I know theta goes from where to where? Anyone? I know it's early.
0 to pi.
Yeah. I want to make sure everybody can see this. I'm trying to expand the window so I can see you, because I got everybody crunched up. All right. I can see John, I can see Fowler. We're on. Yeah, theta goes from 0 to pi, right? Phi goes from where to where? 0 to, people?
2 pi.
2 pi. And where does r go from? This is the important one. Say it again, Tyler.
0 to r.
Okay, exactly right, 0 to r. That's important. So that means I can say d of r here is 1 over 4 pi r squared. And then when I do the first integral, sine theta d theta, I get minus cosine theta. And when I evaluate it from 0 to pi, I get 2. You can do this if you want, but minus cosine theta evaluated from 0 to pi will be 2. After that, I do d phi from 0 to 2 pi, and I get 2 pi. You all with me on that? I'm just integrating d phi from 0 to pi. I get phi evaluated from 0 to 2 pi, and you get 2 pi. Then when I integrate r, I have r cubed, right? R cubed, and I evaluate that from 0 to r. It's r cubed. I'm sorry, it's r cubed. dr is r to the 4th over 4. So I have r to the 4th over 4. And I evaluate that from 0 to r. And then I have also a 10 to the minus 9th operator in there. Correct, class? Everybody?
Excuse me.
Yeah.
Can I put that 10 to the negative 9, like for only the final answer, but not in the equation? Is that still right?
Well, as long as I can see it in the final answer, I'll give you credit. It's a scale. But the only thing is something that scales everything by 10 to the minus 9. Okay. But it had to be there in the final answer. Now, you can see that this 2 pi and this 4 pi cancel. 2 pi times 2 is 4 pi, and the 4 pi cancels. Y'all with me on that, guys? And so what you're left with is d of r is equal to 10 to the minus 9th, and then it's going to be r squared, right, over 4, and that would be for r less than a. Agreed? Now, for r greater than a, part 2, this would be 1. For r greater than a, the thing that changes is on this side, and I'll write it down. When I integrate the integral of d dot ds on this side over the closed surface equals the integral of rho v dv, this side right here, pardon me, this side of the integration, let's sharpen up, come on, is still going to be 4 pi r squared dr. And this is open book, open notes, so there's no excuse to get that wrong. On this side, it's going to be the same as before, a triple integral, where I'm going from 0 to, but not to r, it would be 0 to a, and then 0 to 2 pi, and then 0 to pi of 10 to the minus 9th r times r squared sine of theta d phi, pardon me, d phi dr. Now, the only thing that changed on this side is the limits on the radial integration. It'll go from 0 to a. Does everybody see that, class? And that means d of r here will be equal to 1 over 4 pi r squared. I feel bad I don't have those tests to hand back to you. I've been involved in a bunch of other stuff, and I had to grade some other things because the other class has a test today. But I will grade this as soon as I'm done with you today. Now, this integration, so the integral is sine theta d theta is minus cosine theta from 0 to pi is 2. And d phi from 0 to 2 pi is 2 pi, so you get a 4 pi on the first part, in the first two integrations. Then when I integrate r cubed, I'll put 10 to the minus 9th there right now. When I do r cubed dr, I get r to the 4th over 4, but I evaluate it from 0 to a, so I get a to the 4th over 4. Everybody agree with me? I figured most of you got this right, but I don't know. Y'all remember this as a homework problem? Rho v was slightly different. I'm not sure if I had a 1 over r function in there or what, but it's slightly different. Now, when you do this, the 4 pi's obviously cancel. Then I have 10 to the minus 9, a to the 4th over r squared times 4, or I have d of r equal to 10 to the minus 9, right here, a to the 4th here, and then I have over 4r squared. And that would be for r greater than or equal to a. Y'all agree with that? Now, let me move it back down. Everybody okay with that? I didn't look at them, but I'm betting you most of you got this right. This is a straightforward problem. There was nothing at all tricky about that where you had a region of void and then another layer of charge. But I'm going to tell you on the final exam, what you can expect is some continuous varying charge here, then maybe nothing, and then maybe a sheet of charge, you know, just a surface charge, something more complicated where you'd have to be very clear thinking. Understand, everyone? But the essence of the problem will always be the integral of d dot ds is equal to the integral of rho v, or really the charge enclosed. Doesn't have to be necessarily rho v. Any questions about this problem before I go on, class? Nothing? We good? How many feel they got that right? I'm betting most of you did because I didn't see a lot of ways you could mess this one up, but because you had your notes in front of you. Next problem. And let me show it to you first. Here, I have an infinitely long cylindrical conductor, has an inner surface A, and an outer surface B, and the conductivity between the inner and outer is sigma naught rho, and where rho naught is, or sigma naught is 10 to the 3rd. Determine the resistance. Now, the idea is this, and I want to make sure everybody understands this. The current is flowing from the inner surface at 2 centimeters to the outer surface at 3 centimeters. So it's flowing out in the radial direction. You all see that? It's like a sleeve. It's not flowing down the length of the cylinder, but it's flowing from the inner core to the outer core. Everybody with me on that? Now, oh boy, let me shut my email. So now what I'm going to do is, I can probably do it right here. No, I better do it using the document camera. So now, I'll try to draw this. We're going to assume we have something that can generate a current, and the current will be I, and we're going to connect it to the inner conductor, and then the outer one to the outer conductor. So you have to understand that current is going to be entering this inner cylindrical surface and moving out radially in this direction. So here's the steps. I assume I, and the next thing I need to do is get J. Can everybody see that, class? Right? I'm assuming I is just, J is flowing radially outward. So J is always going to be I over the surface which is the current's flowing through. And if you can imagine this at a radial distance rho, just put another sleeve, another cylindrical sleeve in there, and all the current has to penetrate that. Do you all agree with that? All the current has to flow from the inner to the outer, or it has to penetrate that area, that cylindrical area. You all agree with me? And remember one other thing that I failed to mention. This height I make 1. Anytime you have a choice about what height to use, make it 1. That way you can't mess up. Agreed, class? It's I. What's the cylindrical area here? It would be the perimeter 2 pi rho, right? That's the perimeter of a circle times the height, right? Which is 1. And it would be in the A rho direction. Do you all follow me on that, guys? How many understand that, right? Got it? It's just I divided by the surface area. Now, after I have J, I need to get E, right? And I know E is equal to J divided by sigma. Everybody agree with that? It's the current density by sigma because sigma E is J. So that's J. It's I over 2 pi rho, A rho. And sigma for this one was what? It was 10 to the third, right, times rho. Correct, class? So I'm just going to use sigma naught. So it's sigma naught down there. And this would make that J, or that rho squared. Correct, class? I'm going to just leave it as sigma naught. Y'all see that? That's E. The next thing I need is what? V, right? I need the voltage. So the next thing I need to find is V, and that's the integral of E dot dl. So, and you worry about the magnitude. If it's negative, just, if you get a negative value, get rid of the negative sign. Resistance is always positive. So the voltage would be equal to the integral of E, right, dot dl, or it's equal to, you can put a minus sign on here and go from A to B if you want, but and this would be V BA, and that's actually going to be equal to minus the integral of I over 2 pi rho squared sigma naught A rho dot simply D rho A rho. And here I'm going to go from A to B, and that gives me a voltage V, VA, it would be equal to I over 2 pi as sigma naught, and then integral of 1, the A rho's dot into 1, and the integral of 1 over rho squared D rho is minus 1 over rho. You switch the limits, and you're going to get 1 over A minus 1 over B, right? Because you have a 1 over rho after the integration. You all follow me on that, class? Give me a show of hands. Make sure. Everybody with me? All right. Now, that's the voltage. To get the resistance, R is simply VBA over I, and you just get rid of I. So the resistance is 1 over 2 pi sigma naught times 1 over A minus 1 over B. And then you plug in the specific dimensions and the value of sigma naught. Now the first A was 1 over is 2 centimeters, so it's 0.02. B is 0.03, and sigma naught is 10 to the third, and you turn the crank and come up with a final number. Everybody okay with that? But this is what I wanted to see. Okay. Any questions? You good with that? That was problem 3. Finally, the fourth problem. Determine the electric field in the XY plane at z equals 0 from an infinite line of charge lying on the z-axis, where this is the charge density. The electric field will be in the radial direction only, and you may use cylindrical coordinates. So I give you the value of rho v, rho l, and now I want you to find the electric field in the XY plane. Are you with me, everyone? All right, so for this, I'll put this over here. What I'm going to do is this. first get the doc cam back up. I'll go ahead and try to draw this. I have this is the charge density, rho L, right? And right here, and it's equal to some constant. Hold on. 2 times 10 to the minus 9 times the magnitude of z. Magnitude of z. And now I'm going to come out a radial distance rho. And I know I've already told you I'm only going to have a radial component to this. So I'm after this dE rho. That's what I'm after. But to get it, I take a little chunk of charge here, and I say that charge is going to be equal to rho L times dz. Everybody understand that, right? That's just a little bit of charge. I come down here, and this is the radial distance here, and this will be the square root of rho squared plus z squared. That would be this distance. Do you all agree with that? That would be the radial distance, correct, class? And that means if I get this differential field, this dE right here, this would be dE magnitude, and it would be equal to, and I'll write this down, vector dE, it's going to be equal to dq, right, over 4 pi epsilon naught, and then it would be r squared, right, in the AR direction. Now that's the formal way to do it, right? You take the differential charge, and you divide it by 4 pi epsilon naught r squared in the AR direction. Y'all agree? Right? Now what is r, or what is this? Well, r here, vectorially, would be rho a rho, right? It's from here to here, and that would be minus ZAZ. Do y'all agree with that? Y'all follow me? A point from here to here, or R, would be rho a rho minus ZAZ. Everybody agree with that, class? All right. That means AR, the unit vector, would be R vector over magnitude of R, or that would be rho a rho minus ZAZ over the square root of rho squared plus Z squared. Agreed, everyone? And DQ is just rho L DZ. So that means DE here would be equal to rho L, which is 2 times 10 to the minus 9 times the magnitude of Z here. And then it's going to be dz, that's dq, that's this, over 4 pi epsilon naught, right? And then you're going to have r squared, which is just going to be rho squared plus z squared. Agree with me there? That's just r squared. And now I have to take it and multiply by ar, or I have rho a rho, right, minus ZAZ here. And then I have to divide by the square root of this, which means that's the 3/2 power. Do you all agree so far? That's just setting up the kernel of integration. Correct, class? Everybody? I'm just putting the pieces together. Now, the integration is with dz, and there's an absolute value. The reason I did that is simple, and I know this. When I integrate this, and I'll put the integration sign here and call it E, the integral will go from minus infinity to plus infinity in the z direction. Do you all see that? I mean, your dz. Here's where it gets important to see this. This component, if you just look at what's a function of z, you all see there's a function of z, there's dz, and this is a function of z here downstairs, right? Now this, because of the squaring operation on z, will be always positive. The rho squared plus z squared to the 3/2, that will be strict positive. Do you all see that? But the top part, the z upstairs, will be negative and positive. And because of that, and I know the magnitude of z will be strict positive, it's called an odd function. And I know when I integrate this part, times minus z times dz times magnitude of z over that, I'll get 0. You follow me on that? You can do it with arguments of symmetry, but the z component goes away. You all follow me? How many can see that without me going to further explanation? Okay, you see it, Tyler? Anybody not see it? It's very apparent. If you do the integration, you'll get 0, and you could use anything to do this integration. So I'm left with this. I'm going to have a row times this, and I'm going to just focus on this one. All right? So when I do this, I can say E now is equal to the integral from minus infinity to infinity. Well, 4 pi epsilon naught downstairs, if I take 1 over it, it's 9 times 10 to the 9th. So I have 9 times 10 to the 9th. And then it's times 2 times 10 to the minus 9th, right? Agreed? That's just the constants I've got rid of. Then I have the magnitude of z, and I have rho, and then I have dz over rho squared plus z squared to the 3/2 power. Y'all with me on this? I'm just trying to chomp it down. And I can see these two get rid of each other. So I'm left with 18. And I'll get rid of all that stuff and just put 18 out in front. Are you okay with that, everyone? It's not tricky. It's just getting it down to the essence. And if you want to, you can do the full integration here, but you're going to see the z component goes away if it's in the xy plane. All right. Now, when you do this integral, the rho is a constant. So I can take rho outside, get rid of that. And now when you integrate this, here's the way I did it. You can go from minus infinity to infinity, but you all see this is going to be symmetric. If I have z negative, you'll notice the magnitude of a negative number is just positive, right? It's just going to be whatever the positive value is. And this is strict positive. So really what I can do is this. Just start at 0 and multiply this by 2. 2 times 18 rho out in front. So I have really 36 rho out in front. And now when I integrate this, I'm going to have the integral from 0 to infinity of z over rho squared plus z squared to the 3/2 power dz. Everybody follow me on this? You okay with this? I mean, you can use your calculators with symbolic integration, but you can do it this way too. Now, what I did is I can go ahead and I can let this be equal to u squared. I can have u squared be equal to rho squared plus c squared. And you can do it, you don't have to do it this way. You can use any method of integration you feel comfortable with. And that means 2u du is equal to really 2z dz, right? Because rho's a constant, correct, class? Just take a differential both sides. The 2's go away, and that means z dz is u du, right? And I can go ahead and say that therefore this becomes, or E rho is 36 rho, and that would be the integral from 0 to infinity. Z dz is u du of u du over, and this is u squared to the 3/2 power, or really u cubed. Y'all follow me? It's just substituting. And again, you don't have to do it this way, whatever way you feel comfortable with. You could use a trig identity, I think, in this one too. There's a variety of ways of doing this. Now that's really just what? 36 rho, and this is 1 over u cubed, or I mean 1 over u squared, right? And that would be what? Minus 1 over u. Evaluated, well, it goes from 0, and that means for this one, u, if you have z equals 0, u would be rho, right? And then it goes to infinity. Correct, class? Right? With me so far? Now, because it's minus, I make that plus and just make this upper limit rho and this lower one infinity. And I know that when I have this, my final answer is what? 36 rho, and it's going to be times 1 over rho, because at infinity, 1 over infinity is 0. And you can see the rho cancels, or you get just 36. Or E rho on this one is 36 for all values of rho. All right, so the thing to take from it, doesn't matter where you are in the XY plane, the magnitude of the E field will be 36 volts per meter. Everybody got? Any questions about the exam? The last problem just required a little more, I'd say a little more complicated integration, but the essence was basically just the bias of our, or I'm sorry, Coulomb's law, just the differential electric field doing an integration. Any thoughts, comments? Nothing? I'll have these done today, and I'll have them back to you hopefully before 3:30 today, I hope. All right, now, as far as class today, or the new topics that we're going to cover, I'll just show you where we are. We got done with chapter 3, almost. The only thing we didn't do is one thing. Well, two things, actually. We didn't cover capacitance. And we covered resistance, right? Obviously we did because he had a problem on the test on it. Resistance. Now, the next thing that he has in his book is Joule's law. And this is page 181. Now, I'm just going to show you what this means. It's about power. So first, I'm going to refresh your memories with some stuff. When you think of power in general, like if you have a component, a resistor R, and you have a current I, and you develop a voltage V across there, you know that V is equal to I times R, right? And power is equal to I times V. And this is very basic. Y'all with me? That's just the most basic thing. So if I replace I right here with V over R, then I can get power equals I squared, right, times R, or I can get it V squared over R, either one. These are different forms of the power absorption, right? And the units would be watts. Does everybody remember that from circuits class? Power is voltage times current, or it's I squared R, or it's V squared over R. And this is DC current. We're not talking about AC. How many remember that at least? Right? Okay. Now, when you're, this is called a lumped element, or it means a bulk parameter. There's no dimensions of size. There's just one symbol that's used to represent a resistor. And that resistor could be a light bulb. It could be anything. Doesn't matter what it is. It's something that takes electrical current and turns it into thermal heat or light, one of the two. When we talk about something in a differential mode, we don't use voltage or current. We use H and we use J and we use E. And so when we talk about a differential chunk of anything, we want the actual power that's going to be dissipated per unit volume. It would be dP. Now it's a differential power, and it would be equal to J dot E dV. If you look at the units of this, J has the units of amps per meter squared, right? And then E has the units of volts per meter, correct, class? I just want to show you this with units. Now, when you multiply those two together, you get amps times volts over meter squared, right? Or meter cubed, pardon me. Well, amps times volts is watts, right? And this is per meter cubed. But then we've got we're multiplying it by differential volume. And you can see when you multiply it by the differential volume, that would have the units of meters cubed. Then you get a differential amount of power. Now, here's what you really take from this. I'm just trying to show you by units right here. The real thing is when you want the differential amount of power dissipated per unit volume, you can do it and say it's J dot E right here, dV, or you can replace J by sigma E, and then you get sigma times the magnitude of E squared dV, or you can replace E by J. And if you do that, then you're going to get J squared, right? And then E would be J over sigma, so it would be divided by sigma dV. You all see this, class? I'm just showing you the different ways to write it. And let me just try to expand on this. Really, you can say J dot E if you want, and that's equal to sigma times magnitude of E squared. That's what I usually use. Or it can be the magnitude of J squared divided by sigma. And all these are the differential power dV. Are you good with that? Just give me a show of hands. Somebody see this right here and understand what I'm talking about, right? All right, you do. So I'm going to go ahead and do an example. And we're going to take a look at resistance two ways. The first way is by doing it the classic way, assuming I, calculating J, then from J get E, and after E get V by integrating E dot dl. And the second way is by finding the amount of power dissipated per unit volume and then integrating that over an entire volume. And I know that the power that is dissipated by a resistor is is going to be I squared R, right? Let me show you how to do this, but we're going to back out resistance two ways, and we're going to do it in the classic problem. Please pay attention to this because this is something you have to see. So this is a classic problem. I'm going to go ahead and I'm going to take a long resistor, and there's this value sigma inside here. This is the cross-sectional area at A. It has a radius small a. It has a length L. And I'm going to go ahead and put a battery there between the ends. And it's driving current this way. Y'all follow me? This is a classic one. And what I want is the resistance between here and here, or the resistance of this material with sigma in it. Y'all follow me? Guys? All right, now for that one, the way we did it was we assume I, right? This is a classic. We just make an assumption for I, right? Everybody? Then after I need J. Well, remember, all the current is flowing down here. It's uniformly distributed over that surface area. So J would be I over pi A squared in the AZ direction. Let me give it that Z axis right here. Y'all agree with that? If the current's flowing from here to here and it's uniformly distributed, I take the current over the surface area, right? That's J. Now I need E. And E would be what? J divided by sigma, or it's going to be I over pi A squared sigma AZ. Agreed? And then to get voltage, I simply integrate E dot dl, right, from 0 to L. Since the E field is a scale, it's a constant value, AZ. When I do this integral, really what I'm going to get is what? Just the E field, I over pi A squared sigma AZ, and dl is going to be dz AZ. So you integrate dz, you end up getting Z evaluated from 0 to L is just L. And that would be the voltage, correct? Y'all with me on this one, how I'm doing the class? Just make sure. If you don't, I'll go through any part of the problem you don't understand. I mean, I'm assuming you see it. You good with that, everyone? Now, once I have this, how do I get resistance? It's V over I, right? Correct, class? There's the voltage. I divide by I, or I have L over pi A squared sigma. And that's the classic way of doing resistance. Now, the non-classic way is this, if you're ready. I can say that I can assume I, all right, this is going to be using energy. Now, after I, I'm going to get J is equal to I over pi A squared. You got me on this? But the next thing I'm going to do is get the differential power. And now from there, I know that the differential power is equal to J squared over sigma EV. Do y'all remember that? I did it above. I said it was E dot J or J squared over sigma or sigma E squared. Do y'all remember this, class? How many do right here? You okay with that? Got to make sure. All right, that's the differential power. So I can say this would be equal to J squared. That's that squared. Or I get I squared over pi A squared squared, right? That's J squared divided by sigma. And I know that's the differential power, right? Everybody see that? It's just J squared right here. J is I over pi A squared, so it's I squared over pi A squared squared divided by sigma. That's the differential power, correct? I mean, do you all see it? Now I have to integrate this, that's differential, and I have to integrate this over, and I'll call it dz and the rho, and then it would be rho d phi. Now this is going to be cylindrical coordinates I'm using, and this device under test, if you will, is cylindrically symmetric. So now that's the differential, and I have to do the integration to get the total power. Now dz is going to go from 0 to L, rho is going to go from 0 to A, and phi goes from 0 to 2 pi, and that would be the actual power that's being dissipated by that resistor. Let me move it up again. dz goes from 0 to L, d rho goes from 0 to A, and d phi goes from 0 to 2 pi. Remember, this is a differential element of volume in cylindrical coordinates, isn't it? It's rho d phi, dz, d rho. That's this part. That's differential volume. Y'all agree with this, class? Y'all see it? That's J squared over sigma here. That's differential volume. You all with me? Okay. Now, if you look at this, when I do this, nothing in here is a function of rho, z, or phi, is it? Right? Nothing in there is a function of either of these. So when I integrate z to get the total power, and integrate dz, I mean, I'll get z evaluated from 0 to L is just L, right? Then when I integrate d rho times rho, that's this part, I get rho squared over 2. Agreed, class? From 0 to A would be A squared over 2. That's this integral. Because I had rho there, and then d rho. When I integrate d phi from 0 to 2 pi, I'm going to get 2 pi, right? And then I have to put in this kernel of integration, which means I have to put in I squared over pi A squared squared divided by sigma, and that would be the power. Y'all follow me? Now, what do you know about power in terms of current for a resistor? Well, power is equal to I squared R, isn't it? Y'all agree with it? Can you all follow me? I'm sorry if this thing's, I don't mean to have a thing fade like that. But you all see how I squared R would be equal to the total power, right? Now, the thing you'll notice is the I squareds cancel. And when you're calculating resistance, it will not be a function of current unless it's a nonlinear resistor. And all the materials that we study, they're linear. It means the resistance value has nothing to do with the current that's flowing through it or the voltage across it. And that's consistent with everything you've been taught in your laboratory work. So what do you see it becomes? Resistance, or this is I squared over times R. When you look at this carefully, what do you end up getting? You get L, right? And then the 2 cancels right there. You got an A squared times pi here. There's an A squared pi. It's pi A squared squared, so I have divided by pi A squared, right? That gets rid of this stuff. And then divided by sigma is R. And lo and behold, that resistance right here that we use by calculating first the energy, or I'm sorry, the power dissipated, differential power dissipated, and then integrating that over the entire volume to get the total power dissipated, and setting the total power dissipated equal to I squared R. This resistance we got that way is the same as the resistance we've got by assuming I, then J, then E, then V. So either one A will get you the same resistance. Can you all see this, class? I mean, this resistance right here, y'all follow me? This was done using power, differential power, and calculating total power and equating it to I squared R. The other way, we calculated resistance by assuming I and then finding V and noting that R is V over I. Either way will get you the resistance of the material between the plates. And this is a classic way to do it. You could do it for concentric spherical surfaces. You can do it for cylinders where you have current flowing from the inner to the outer radius, but you can use either method. Now, the real thing about power dissipation and volume, the reason it's important is that whenever you're dissipating power, it usually goes to heat. It goes to thermalizing and just heating up an area. Well, when you have heat, unless you have a heat flow and some way for heat to flow off, the temperature keeps going up and up and up and up. And eventually something's got to give. Either there'll be a fire or there'll be a stress crack or something like that. So as electrical and computer engineers, one of the things you look for when you're doing microelectronic component development or putting things on boards or VLSI design, you always have to have two sets of equations that you use. One that dictate the electrical behavior and everything like that. And the other is thermal behavior, because you want to make sure that things don't thermally get too hot. Now, have you had thermodynamics yet? You haven't? Well, some people have. In thermodynamics, you have Boyle's law, PV equals nRT and things like that. But you'll have sets of equations that describe the thermal behavior of a region that you have to model simultaneously with the electrical equations in order to find out if, in fact, the components that you've put together or the device you're building, if it will or won't go into a thermal stress or have problems. And that's very important because, as we all know, anytime you have something that's got current flowing through it, you get heat. Your computer, anything like that. And heat dissipation becomes the limiting factor a lot of times in what, you might say, in the performance of any device. And I use that in a loose way, but performance generally means how well it does what it's intended to do. And there's all sorts of figures of merit they use. Okay, that's Joule's law in a nutshell. Now, we covered dielectrics. Y'all remember? Oh, I'm sorry. We didn't cover dielectrics, but I mentioned this a couple of times. When we think of dielectric materials, the thing that comes to mind is insulators. Off the top of your head, if you had to, if you were asked this at a job interview, what are some good insulators? John, can you give me an example of any? And Tyler and Ben, I'm going to ask you as well as Caleb.
Rubber, styrofoam, wood.
They're all good. They're things that will prevent electricity from flowing through them. And your wires from your extension cord are usually, they're encased in plastic or really maybe a rubberized product, something like that, that prevents electricity from flowing from one conductor to the other. That's all they are. Well, they're also termed dielectrics. An insulator is a dielectric. And the way a dielectric really works, if you look here, inside of dielectrics, almost all, except for liquid dielectrics, this doesn't quite hold true. You're going to have things that are bound, molecules that are bound in place that can't move, or you could say atoms in this case, but really these are molecules. They're not just single atoms, and they have a net positive center and a net negative center, and the net positive and negative centers are very close if there's no electric field. But the minute you impress an electric field on them, the positive centers move in the direction of the electric field and the negative centers move in the opposite direction, or the actual molecules stretch. And just like a spring, when you stretch something, if you remove the electric field, it goes back to its original state. Right? That's the way it works at the molecular level. Now, as you're stretching these things, they're gaining energy. And when you remove the electric field, that energy will be put back into the lattice and be manifest as a voltage. But the way we deal with this, try to understand, this is the way we deal with it, not a material science would. We create something called epsilon relative. And we say that D, y'all see equation 3.99 that I'm pointing at here? Can y'all see that? D is equal to epsilon relative times epsilon naught times E. Epsilon naught is just the value of the permittivity in free space. Epsilon relative tells you how much better that material is than free space at storing energy. Now, I'm going to give you this. Wentworth does it from a material standpoint. He says, really what D is epsilon naught E. That's the electric field in a vacuum plus something called a polarization. I don't do it this way because polarization is never used for anything except materials engineering, in my opinion. So I don't even bother with that. And then he's going to say, well, D is equal to epsilon naught times 1 plus chi E, and chi E is the P. So here, the polarization is chi times the electric field, but don't worry about that. The thing you worry about is right there, epsilon relative epsilon naught. Now, or we just call it epsilon, which is epsilon relative times epsilon naught times E. I got to talk to you about this for a second. So I mentioned energy several times, but Wentworth doesn't talk about this. Y'all know that we talked about the power dissipated per unit volume, right? Now, I gotta see if he has it here. Give me 1 second. Yeah. If we have the differential energy, the symbol is usually WE or work. The differential energy per unit volume, this is going to be energy per unit volume. That's equal to 1/2 epsilon times magnitude of E squared, or it's equal to 1/2 and then it would be D squared. By the way, D is equal to epsilon E. So if E would be equal to D over epsilon squared, and that means it would be D squared over epsilon. And the units of these are, are joules per meter cubed. Do y'all follow me on this? Now this is energy. And here's what I want to take you to take from it. If you take a look at the differential energy per unit volume, right here, it's equal to 1/2 times epsilon E squared. And you can see that the amount of energy a material can hold is linearly proportional to epsilon. If you just have epsilon naught or a vacuum, you have 1/2 epsilon naught E squared. But if you have a material with epsilon relative greater than 1, then really it's saying how much more energy for a given electric field can it store in that region. Does that make sense to everybody, class? So that's the way I like explaining epsilon relative. There are other ways, but it's really, for an electrical and computer engineer, from our perspective, it's telling us how much better that material is than air at storing energy. So how many have heard of supercapacitors? Anybody? One? All right. Let me give you a tip here. This is something on the future. We're not there yet, but you know, a capacitor is an energy storage device, right? You charge up a capacitor, you got energy in there, and if you discharge it through a resistor, you take that energy and dissipate it as heat through a resistor. Now, energy is something that's, everybody's looking at ways of storing it for a lot of reasons. Normally, if we talk about something that's going to have a lot of energy per unit weight, we look at a battery, either a lithium ion battery or a lead acid battery, and you're familiar with those. Your laptop has a lithium ion battery in. They can store a lot of energy. You can't get it out very fast, but you got a lot of energy in there. Right? Even if you're dead short a battery, it's still relatively short. I mean, excuse me, a rather long time for that thing to discharge, totally. But if you have a capacitor, you can get energy out very fast. The problem is with a capacitor, we can't store that much energy. Well, with supercapacitors, what they're looking for is they're creating epsilon relatives that are extremely high. So that if you think about the capacitance, and we'll be doing this, the capacitance will be proportional to epsilon relative, and we'll see that in a second. But what they're trying to do is get epsilon relatives of maybe 100,000 to 1,000,000. That means a capacitor that normally would store maybe a microjoule would store a joule of energy. That's a large amount, by the way, a joule. Now, what they would like to do is have supercapacitors made with these exotic materials, supercapacitors that could be used to replace batteries. That's sort of the goal. But a battery is so much more energy dense per unit weight, or mass really. The batteries, lead acid or lithium ion, they have so much more energy that they can hold. And the other thing with a dielectric that I haven't mentioned, or an insulator, there's a thing called breakdown voltage. It's what voltage can it take before, or I should say, what electric field can it take before you actually get an arc? Now, you know in air that you see static electricity sparks, or you see sparks jumping whenever you have touch wires together. You're familiar with that, right? Or arc welding, or lightning. Well, what's really going on is that whenever you see an electrical spark, you see ionization of the atmosphere, and the light being emitted is basically the electrons falling back into their rest state, and they're emitting a photon of light. They're being ripped away from their rest states, and then they relax back into it, and that's what the photon comes from. So in order to do that in the just standard conditions in the atmosphere where you and I are living right now, it takes about 3 million volts per meter. Well, 3 times 10 to the 6 volts per meter on 2 parallel plates would do it. With dielectric materials, you would like the breakdown electric field strength to be much, much greater than that. Instead of 3 million volts per meter, maybe 300 million volts per meter, like with a good insulator. Maybe 10 to 15 times, or maybe 100 times what the atmosphere has. Do you all follow me? So that would allow much more energy to be stored per unit volume before it arced over. So that's something called the electrical breakdown strength of an insulator or a dielectric. And you want it as high as possible. And that's also something that materials engineers try to create, these materials that will have enormous breakdown strengths. And there's a whole lot of stuff I can tell you about. When I was in grad school, I had a guy named, not Rustam Roy, but Leslie Cross, and he was a brilliant professor on the National Academy of Science, or National Academy of Engineering. And he had a whole course in really in materials engineering that focused on the electrical and the mechanical properties, and how to engineer materials to get the desired benefit that you want. But the problem, a lot of this is you have to have a lot of chemistry and a lot of actual fiber engineering, or I call it ceramic science and fiber engineering background, because there's so much that rests in your understanding of the periodic table and other things that if you get into grad school, you'll find out about in a hurry. Just keep that in mind. Those materials we're on the cusp of getting some exotic materials for supercapacitors. And if you get involved in a company with that, you might really have, you'd have something very interesting to investigate for years and years and years. And I don't know where it's going, but that's what I can tell you about. Now, the next thing that we haven't covered is capacitance, right? I'm just about out of time. I'm going to start. How many have heard of the term capacitance? God, I hope you all have. If you haven't, you haven't taken physics. Your physics professor should have done a fair job at making you aware of what capacitance is. And so when we talk about capacitance, what we usually do is start by showing a symbol. And a capacitance is just 2 parallel plates. They usually show it like this. This is your circuit's example of what a capacitor was, right? What a capacitor really is any 2 conducting surfaces. And they could be planar plates of metal, it doesn't matter. Any 2 surfaces, you can have a differential voltage across them, and that means they'll support plus and minus charges on either side. And they'll create an electric field between them. Now that electric field is where all the energy is stored. Follow me? And the energy we just talked about is 1/2 epsilon E squared. I mean, that's the energy density per unit volume. That's the symbol for a capacitor. Normally, if we talk about capacitors, I mean, they can look like this, or they could be cylindrical sleeves. You could have basically something like this, where you have a long inner conductor this way, and then you have an outer conductor here, and it's separated by some epsilon. I hope you can appreciate what I'm trying to draw there. I'm trying to draw two concentric cylinders. On the inner surface, you're going to have a conductor. On the outer surface, you're going to have a conductor. And in between them, you have an insulator or a dielectric. That's another capacitor. You could have a spherical capacitor, where simply you have an inner radius A and an outer radius B, and you put some epsilon between them. Y'all follow me on this? These are the different geometries that are typical. But in all cases, you have two surfaces that can support a differential voltage, and one will have positive charge, the other will have the same magnitude but negative charge, right? That's basically what a capacitor is. Now, the next thing is, well, how do you calculate the capacitance of any geometry? And the way you do it is very similar to the way you calculate resistance. The first thing you assume is usually the charge. You can assume the voltage if you want. You assume the charge. And we're going to do a problem real quick before I let you go. Once you assume the charge, you can get the D field, because these are for highly symmetric shapes. So after you have Q, you can get D. And D is always equal to Q over the surface area, right? It depends on the area. If it's spherical, if it's cylindrical, if it's planar. But it's charge divided by area gives you the D field. Doesn't it, class? You remember this, right? You remember from Gauss's law. Yeah, Gauss's law. Then after D, you get E. And E is just equal to what? It's equal to D over epsilon, isn't it? Class? Right? Now, once you have E, then you get V, and V is equal to the integral of E dot dl, right? And finally, you get C. Now, how many remember these formulas that C times V is equal to Q? Do you remember that one? Capacitance times charge, or times voltage was charged. How many do? Anybody? No? You remember for resistance, right? That voltage was equal to I times R. You all remember that one, right, guys? Well, this is the same thing, only it's for capacitance. Q, the charge on one plate, is equal to C times V, where V is the voltage between the plates. Does anybody remember this one? I'm kind of shocked you don't. In physics, they usually drum that into you. I don't think Irwin used this much in his class. If you had Dave Irwin for circuits, he uses V equals IR all the time. You'll have that one, but you'll have it down. But Q is equal to C times V, and that's important. Now, the next thing I'm going to tell you is the way we do capacitance problems, we assume a charge, get D, from D get E, from E get V, and finally, we get the capacitance by taking V over Q. Make sense? Oops, sorry. Yell at me if you can't see. If I need to move this paper over. I'm trying. All right, so how's about we do a simple problem before we leave today, just to start you off. And then it's going to be a classic problem. By classic, I mean it's done in every textbook probably on the planet. And probably you had this one in physics. Are you ready, guys? So here's what we're going to do. It's going to be a sphere. It's a spherical capacitor. So I put an inner radius A, right? And then I have an outer radius B. And in between them, I have some epsilon relative. Or I have some epsilon. Just call it epsilon. Doesn't matter. Now, here's what I do. I bore a little hole right through there. And you attach a potential, make it a positive voltage. And then on the outer surface, you're going to metallize it. And you can ground that for all intents and purposes. So you got a perfect conducting surface at B and a perfect conducting surface at A. And in between them, an insulator that has a value epsilon. You all follow me so far? Got it? So here's what we do. We're going to assume that we have a plus Q on the inner plate or the inner surface and a minus q on the outer surface. Are you with me? We're going to assume the charge and calculate the voltage is what I'm getting. And it's always, almost always that way. You assume q. Now, the next thing I said was get d. You all agree that the units or the coordinate system we should use is spherical, right? So if this is right at the origin, right here, then if I come out a distance r, my d field right here would be equal to q over 4 pi r squared ar. You all agree with that? That's just the charge over the surface area. And the surface area of a spherical shell at a distance r away would be 4 pi r squared. You agree with that, everyone? Let me finish this thought and I'll let you go. I'm trying to make sure we're staying at rate because we missed 2 days when we had those finals and that mini semester really hurt us. We didn't have those 2 days for lecture. Now, after I get D, how do I get E? Anyone? John or Tyler or Carlin or Fowler or Yancy Wang or anybody?
D for epsilon.
Yeah, I divide D by epsilon. So that means Q over 4 pi epsilon naught R squared AR. That looks very familiar, doesn't it? That's the chart. That's the electric field from a point charge, isn't it? But here it's an entire amount of charge we put over a surface, but that's still okay. You with me? Now, after that, we need to get V. And V would be the integral of E dot dl. And you always take the positive value because if it becomes negative, don't worry about it. Just make it positive because the voltage is a strict positive with capacitance. It's voltage over, if you take voltage, right, and divide it, or we know voltage times capacitance is Q, so you take Q over V and you get C. But this is going to be the integral of that. So that means my results will be what? Q over epsilon naught, or 4 pi epsilon naught, pardon me, 4 pi epsilon naught. And then when I integrate R squared AR dr AR, I get minus 1 over R between A and B, and I'm left with this. 1 over A minus 1 over B. Think about that. R squared AR dr, dl would be dr, AR would be 1 over R squared integrated is minus 1 over R evaluated from A to B. And it would be 1 over A minus 1 over B. Y'all see this, class? Give me a show of hands if you do. If you need me to go through more about the integral, but it's a straightforward integration. Now that's equal to V, and I said capacitance was equal to Q over V, right? Now I'm going to make sure you see this step. I'll put Q here, and this is V. So V is equal to Q over 4 pi epsilon naught times 1 over A minus 1 over B, right? Please be careful on this step. Y'all see how the Q's cancel, right? And they always will. Capacitance will never be a function of charge unless it's a nonlinear capacitor. And that means the capacitance for the simple one will be equal to 4 pi, and not epsilon naught, but epsilon over 1 over A minus 1 over B. I want to caution you about something. I have seen this over and over again. I will see people, when they see this right here, for some reason, when they invert this, they'll have 4 pi epsilon naught A minus B. They'll make silly mistakes on this math. Remember, that's 1 over A minus 1 over B, and that stays in the denominator. You okay with that, everyone? So that's an example of how to do simple capacitance problems. And I'm going to give you some of those. I'm going to give you a few problems for this Wednesday, and I'll get your test back today sometime. And I apologize for not having this for you today. I was a little busy with other things. Okay, guys? All right. We'll see you on Wednesday. You'll get more homework, and